Okay, let's get going. So this week we're going to continue talking about probability theory using discrete random variables. Next week we'll get into the probably more useful case of continuous random variables. In the meantime, we have to go through this again. The employee of Columbia gets lots of money to develop Stan. A use stand is part of a LLC, and that creates the appearance of a conflict of interest if you're expected to earn more than $5,000 per year that you should be aware of before learning probability with discrete random variables. Another thing, Piazza. Less than half of you are actually signed up on Piazza for this course, and that is not even remotely close to acceptable. Remember that 1/6 of your grade is based on class participation, and the stuff on Piazza is the only thing that actually gets sort of objectively recorded, how many questions you ask and how many you answer and stuff like that. Yeah, there's basically been one countable post. So if you are not Nathan number 2, you're in the hole in terms of class participation, but you're also in the hole in terms of your understanding. We're talking about the most contentious issues in probability. We're learning sort of the math behind probability at basically double the speed that you would ordinarily learn this in order for us to be able to get to the Bayesian estimation stuff with Stan for the rest of the semester. There's not currently, but shortly after class, there will be a poll on Piazza asking about preferred times for an optional extra session on Monday, which was the only time that we could get a room. You don't have to come to this, but what it will cover is how to create and knit our markdown file, which is the way in which we'll be doing homeworks in this class. Certainly, if you've done a class that I've taught before, you would already know how to do that. So even if you want to show up, you don't necessarily need to show up for the first part. Second, making sure that everybody has the RStan R package installed and the supporting C++ toolchain. This is more involved than just installing a regular R package, but you need to do it on your own laptop. So you can click on this link, which will have the instructions for how to do all that. But in the extra session, if you're having trouble, the TAs will be able to help you. And maybe for the last half hour or so, there'll be a review of some of the stuff that we're talking about today, last week, also on Thursday, involving probability distributions with discrete random variables. So we're not going to be having these extra sessions every week. We'll probably have a few of them over the course of the semester. Like I said, you don't have to come, but if you want to, there'll be a poll asking you what times you're available, but it's basically just Monday morning. I think we'll try to YouTube those as well for those of you who can't make it. But anyway, that will be on Piazza shortly after class today. Questions? Right. Save them for Piazza. All right. So if you source in this URL, it will bring in the R code that we did last week, which creates this 11 by 11 table where each interior cell here represents the probability of knocking down some number of pins corresponding to the row for your first roll and some other number of pins corresponding to the number of pins you knock down on your second roll. So this right here would be the probability of knocking down 5 pins on the first roll and 5 pins on the second roll, and that number according to the assumptions that we were using last week, is about 0.013. Okay. So first of all, who can tell me how all these interior cells of this table were constructed? What did we do in order to generate all these different numbers? Last week. Andres. Uh-huh. Right. So we had a formula for the number of pins to knock down on the first roll. So that would get us that. Then how did we figure out the number of pins knocked down on the second roll, or the probability thereof? So we had a function for the marginal probability of knocking down some number of pins on the first roll. We had another formula for the conditional probability of knocking down some number of pins on the second roll, given the number of pins that were knocked down on the first roll. And then what did we do with those two functions in order to compose the table? Merlin?
The joint probabilities and multiply the first row and number come down times the conditional probability and a certain amount on the first row.
Right. So we multiply marginal probability, number of pins knocked down on the first roll, by conditional probability, number of pins knocked down on the second roll, to obtain the joint or the bivariate probability of knocking down x1 pins on the first roll and x2 pins on the second roll, where x1 corresponds to a row index, x2 corresponds to a column index. Questions about that? Okay. So according to this table, how would you come up with the probability of knocking down 3 pins on the first roll if I don't give you any additional information? Robert?
The sum of the probabilities row.
Or the one that has label 3.
Yeah, right.
So all this over here. You do what to them?
Sum them.
Right. So that's the application of what rule? Addition rule. It's not particularly difficult, but it goes along with the general multiplication rule that we use to compose these probabilities. So what in general is the general addition rule say? Sebastian. Is that you? The wrong name? Yeah. Okay. Well, answer the question anyway.
So you take the probability A and sum it over each level conditional on. So B was the second row. You would sum the probability of getting 3 conditional of getting 0 for the second row plus conditional of 1, 2, all the way through the end.
Right. So we can add up these things, and it's pretty simple when the things are mutually exclusive. So you can't knock down, 3 pins on the first roll, 2 pins on the second, and 3 pins on the third. So the mutual exclusivity helps us here. But what does the general multiplication rule tell us when we have events, let's say A and B, that are not mutually exclusive of each other? How do we come up with the probability that either A is true or B is true? Becca.
The probability of A plus the probability of B minus the probability of A.
Right. So the probability of A and B you have to get from the general multiplication rule. But in a lot of cases, including of this, there's situations where A and B are disjoint, mutually exclusive. That third term is 0, and you can just add pairs of things together, and you can extend that to 11 different things that are disjoint. Okay, so the probability of knocking down 3 pins on the first roll is the sum of all these numbers in gray here. So how would we figure out the probability of knocking down 3 pins on the first roll if someone told you that they knocked down 4 pins on the second roll? Merlin.
Down 4 on the second, in the first, then divide by marginal, the number of events. But by the marginal probability of having struck down 4 on the second.
And how do you obtain the marginal probability of knocking down 4 on the second roll? Summing what?
Sum the column.
Sum down the column. All right, so we take this here at the intersection of 3 and 4, and we divide by the sum in the 4th column. And this is what's known as Bayes' theorem. And this is a specific instance of the more general thing that we want to do, which is get the probability of whatever we don't know, in this case, how many pins were knocked down in the first roll, given what we do know, which is the number of pins knocked down in the second, which is 4. So we're going to be using Bayes' rule not a lot, but we want to certainly develop a lot of the intuition behind it. So if I don't tell you anything, the probability of knocking down 3 pins on the first roll is just the sum here. And the sum over the whole table is going to be 1. So we sort of have, the sum of this relative to a total of 1. But if you get additional information that 4 pins were knocked down on the second roll, that you're in column 4, or the column with label 4 somewhere. Could have been 0 and 4, could have been 1 and 4, 2 and 4, 3 and 4, 4 and 4, 5 and 4, 6 and 4, and then the rest are impossible. So when someone tells you 4 pins got knocked down on the second roll, all this probability over here, all this probability over there, that didn't happen. You're just in this one slice. And these joint probabilities are proportional to conditional probabilities. So if we know, none of this happened, none of that happened, it's only something that happened in column 4, then it's going to be one of these numbers. It's got to be one of these things. But these things together don't sum to 1. So by itself in column 4 is not a valid probability distribution. We need all the possibilities to add up to 1 in terms of their probability. So what we do is we take these and divide by their sum. And now that ratio is going to sum to 1 over the entries in the column labeled 4. So we renormalize these joint probabilities so that they add up to 1 when making conditional probabilities of knocking down this or that number of pins on the first roll, when knocking down 4 pins on the second roll is known. So we basically start off with, all we know is this, the joint probability table, and then, we have a marginal probability, etc. But when we get additional information, we need to update our beliefs about the probability that the number of pins knocked down on the first roll was 3. And we do that by taking, all this probability of stuff that didn't happen and, basically merging it into column 4. Because the sum of column 4 is equal to 1 minus the sum of all the other columns put together. So we're basically dividing all this by 1 minus the sum of all the probabilities that didn't happen in order to renormalize these joint probabilities into conditional probabilities of knocking down these number of pins on the first roll, given that 4 pins were knocked down on the second. And so Bayes' rule, particularly in the case of a discrete random variable like bowling pins, can really be seen as reallocating probability across the sample space. So originally it was all this, And then when we know 4 pins are knocked down in the second roll, we can reallocate to get a conditional probability distribution for the thing we don't know given what we do know. Questions about that? All right. So we can ask the same thing about other questions not having to do with bowling, such as what is the probability, or what do you believe is the probability that the Patriots beat the Eagles in the Super Bowl? That's something that you don't know today who is going to win, but you might have beliefs about the probability that one of the other teams is going to win. And this is an example of a question that a frequentist, at least a strict frequentist, would say it's not feasible to answer a question like this objectively. And at least, you know, if you're studying football scientifically or something like that, you should not answer this question subjectively. Because the only way in which you could objectively answer the question from the frequentist perspective, what is the probability that the Patriots beat the Eagles 2 weeks from now in the Super Bowl, is to have the Patriots and the Eagles play like 1,000 games. And then the proportion of times that the Patriots win is the probability that the Patriots win. And it's almost a sort of circular way of defining probability. But at a minimum, it's saying, well, the probability is sort of a property of the Super Bowl. And we can only figure objectively what it is by observing that happening over and over and over again. Now, not going to happen. They're going to play exactly one Super Bowl in 2 weeks between the Patriots and the Eagles. So this whole idea like, well, let's just have them play 1,000 times is completely useless hypothetical. Moreover, in the case of a Super Bowl, it's not even something that we could really imagine 1,000 independent Super Bowls between the Patriots and the Eagles happening. You know, people get injured and they might miss the next 30 Super Bowls. The Super Bowls wouldn't be independent because the teams are going to adapt to each other's strategies between the 16th Super Bowl and the 17th Super Bowl. So not only is this not going to happen, it's basically impossible to imagine this hypothetical experiment that frequentists insist on in order for you to have objective beliefs about football. You might question, well, do we really need to have objective beliefs about football? Could we just have subjective beliefs about football to answer things like what's the probability the Patriots will win? And one way of understanding this from a Bayesian perspective is by thinking about betting. So if you would be willing to risk $3 such that if the Eagles win, you get back your $3 plus an additional $7, that means that you subjectively believe that the probability that the Eagles will win is greater than 0.3 because you're willing to bet at 7-3 odds, where odds is simple, relatively simple function of, you know, the probability of something being true. If you're not willing to risk 3 to gain 7, you might be willing to risk 2 to gain 8, in which case you think the probability that Eagles win is between, you know, 0.2 and 0.3. And this is one way of interpreting Bayesian stuff that's often attributed to a guy named Bruno De Finetti, an Italian economist, statistician, a lot of different things, who basically said, well, you can interpret Bayesian probability through, you know, what you're willing to bet on. And sometimes you have to, you know, elicit a bet in order to understand what someone else's probabilities are. And so in that way of thinking, this is just sort of an efficient way of communicating your subjective beliefs versus using probability. And so if someone says, the probability the Patriots beat the Eagles is, greater than 0.5, I think everybody understands what that means. Even people who, not enrolled in the QMSS or whatever. If you just wander out on Broadway and you ask somebody, what do you think the probability the Patriots are going to win the Super Bowl? It's not at all inconceivable that they would be able to give you an answer, even if they don't know really how to use Bayes' rule in order to update their subjective beliefs as new information comes in. But they have this sort of informal process based on all the information that they've seen, about the football season so far, that they'd probably be able to come up, with some sort of number describing their probability. And, might ask the question, well, why does science or policy or anything like that have to be different in the way that we think and communicate with probability than football does? But basically, under the point here, basically frequentist probability has no answer to questions involving proper nouns. You might be able to come up with something like if we randomly took, a whole bunch of football games and analyzed them, you could, come up with something. But for a football game between the individuals who comprise the Patriots and the individuals who comprise the Eagles currently, like this one game that is coming up in 2 weeks, that's just out of bounds from the frequentist conception of probability, which is, the number of times something occurs in an infinite number of independent repetitions. Questions about that? Anybody willing to risk 3 to get 7 on the Eagles? Yes? All right. Good.
We're doing it right now.
Oh, we are doing it right now.
I don't know if I have one.
You want to risk a 20 to get 7 on the Eagles?
Oh, no,
Who wants to hold on to the official money? Very important. Andre, do you trust this guy? All right. Come back in 2 weeks. Does everybody understand what just happened? No great mystery. Oh, you have a question about what just happened?
Yeah.
Okay. Yes. So I did not ask whether you want to bet 3 million to win 7 million on the Eagles. That would involve stuff like risk aversion and stuff like that. But for small amounts of money, we're basically going to assume constant utility there. Becca?
Unrelated to that. Well, vaguely related. Is there like a value in you saying to me like, okay, well, would you do 4 for 7? Okay, so we know it's between 3 and 4. Would you do 301 for 7? So we know it's like
Definitely.
narrow.
So it's not just the case that you have like one probability that you know for sure the Eagles are going to win. You have some like distribution over that probability that might be centered, around 0.4 or something. But you don't even think the Eagles are favored, do you? No. Okay, so it's less than 0.5 and more than 0.3. Okay. So we've learned something about what Becca believes today. Not the worst thing in the world. Andres.
Reason it's hard to understand like planning paradigm to policy when some things are hard to conceive in monetary terms.
Yeah, it's part of the challenge is specifying what is your utility function. More straightforward if we're just talking about a business, basically you can take it to be profit. But if you're talking about something like what's the objective function of a central bank, harder.
lot of us refuse to take that. You know,
Oh, well, you think the probability the Eagles win is less than 0.3? That's possible. You don't have $3, also possible. But yeah, those are, or you're irrational. That's about the only 3 possibilities, I think.
would you be able to update what? I guess if you were able to change what the.
Yeah. So if, you know, Tom Brady cuts his hand open again during practice and it like is amputated, then you could update your beliefs about whether like Tom Brady can win the Super Bowl throwing with his left hand. So it might be, you know, closer to 0.6 or something then. Sure. Nicole?
They have to be rational beliefs. Like, what if I think that Tom Brady joined the Illuminati and
Yes. So that's one of the things that people criticize about the Bayesian thing is that you can come into it with absurd beliefs. And there's nothing really Bayes' rule that like requires you to come in with reasonable beliefs. It just requires you to come in with quantifiable beliefs. And then Bayes' rule prescribes the objective way to update irrational beliefs or things that were, you know, to some extent based on reality or, you know, other whatever. So it's not a, this is the objective thing to believe. This is the objective way to update your beliefs. That hopefully yields some convergence, but you can certainly persist in believing, you know, crazy things if you have sufficiently strong beliefs that are crazy originally. Yes.
So as a counter to that, I feel like isn't the argument against skepticism like that? So here it's very obvious that it's outside of their scope. Isn't the argument that very often they kind of keep yourself starting because you can never attain the conditions where it's possible, or it's Bayesianism to acknowledge the fact that there's something.
Certainly with the Bayesian thing, you have to acknowledge that there's subjectivity in it. I think with, you know, frequentist thing, even if you can do like a model or whatever, there's still a question, okay, what variables go into the model? What are the hypotheses being tested? What models are you comparing? And all of those choices are made by a human. So I don't think it's correct to say that the frequentist approach is devoid of subjectivism. But with the Bayesian approach, you're sort of explicitly injecting your beliefs through the first term on the right-hand side of Bayes' rule, the prior distribution, what you believe now, and then as you get more data, you update it. Other questions? All right. So now next thing to talk about is the expectation of a discrete random variable. And the expectation is something that is contrasted with the mode and the median. So we want to keep those terms distinct. So the mode is the element of the sample space that has the highest probability if there is such a unique value. And the median is the smallest element of the sample space such that at least half of the cumulative probability is less than or equal to that element. So in the case of bowling, where here is the marginal probability for the first roll of a frame of bowling, what would be the mode? Ellen. Wait, 004. So the one with the highest?
Oh, the highest. Oh, sorry.
These two are the lowest.
Yeah.
So which one's the highest?
The last.
10, or a strike. So this probability distribution is constructed that a strike is the most likely thing to occur out of the 11 possibilities. All right. So what would be the median for the number of pins knocked down first roll of bowling? Shereen? Question?
Is the mode going to be 10 or the mode is 0.3?
The mode is 10. The element of the sample space. So what element of the sample space satisfies the definition of a median? Believe?
9.
9. And how did you come up with that?
I just took 9 and 10 together are over 50%. So that means like the left, the lower side, so that includes those.
Right. So we've got 0.384 for 10 and 1 minus 0.384 for everything else. But 0.237 and 0.384 is more than 0.5, so we know the median is going to occur on 9. Okay? Now, both the mode and the median are, in a manner of speaking, descriptions of the center of a probability distribution for some definition of center. But the most common way of conceptualizing the center of a probability distribution is through its expectation. And expectation is a weird word in English that means something a bit different than it does in statistics. So you basically just have to memorize this definition for the expectation of a discrete random variable x that is defined as the summation over the entire sample space of the product between little x and its probability. So in this case, it would be the sum of 11 different things. Take each one of these values of x, multiply by its corresponding probability, add up all those products, and that is the expectation. And the expectation is so fundamental in probability that it has its own Greek letter, which is, Christina, thank you, mu. So you literally have to just memorize this definition of the expectation of a discrete random variable, the sum over the whole sample space of the products between each element of the sample space and the corresponding probability. So expectation is really just a probability weighted sum. We take the value of the number of pins, multiply by its associated probability, and then we add all that up to get what's known as the expectation. This example we did with the marginal probability, so it's a marginal expectation. But if you use conditional probabilities in that process, then you have a conditional expectation given something that's already happened, something that you know to be true. So you can use conditional probabilities to get a conditional expectation. Okay, so you may have associated the expectation or mu or whatever with the sample mean. And the sample mean is an estimator of an expectation. So here we have the expectation for some random variable y defined here. So let's say, what if we estimate the probability that the random variable is equal to y with this function here, the sum over like n observations of the indicator function, when is the nth observation equal to y? So we're estimating the probability that the random variable is equal to y with the proportion of times that it's equal to y in our sample of n observations. So if we use that as an estimator for the probability, plug it in. So we have, this part over here, this over there, pull the 1 over n out front. We have two summations. The first one involves, or the second one has y being constant here, and it's summing over the observation. So we can move the y over. And now we have a double summation of y multiplied by its indicator function. And you can see, if you think about that for a second, that that's just going to be equal to 1 over n multiplied by the sum of the n observations that we have in our sample, which is what you probably learned before as the definition of the sample mean. what you probably didn't learn is that the sample mean is the estimator of an expectation of a random variable or a function. An expectation is a property of the function that you're estimating with data. Now, if you have a representative sample of observations, this is not a ridiculous thing to do. If you don't have a representative sample, then this is not going to be a really good estimator of some unknown probability of y occurring. And so with data, it can be difficult or expensive to get representative samples. What we're going to be doing more of this semester is drawing things from probability distributions, which I'll indicate with a tilde over the top of it, that this is drawn realization from some probability distribution for y. And if we do this capital S times and let s go to infinity, then the sample mean evaluated at realizations of y from its probability distribution is going to converge in probability to the true mu for the random variable y, the true expectation for y if we're drawing an infinite number from the probability distribution for y. Now, of course, we're not going to literally take an infinite number of realizations with a finite computer, but if we do, 100 million or whatever, we can get the expectation for the first roll of bowling correct to 3 decimal places, which is, probably 2 more than we need. We're going to run into situations very soon where it's not going to be possible to calculate expectations and things like that exactly. So we're only going to be able to use a large number of simulations, but that's going to be fine as long as we have a way to draw these things from the corresponding probability distributions, and those probability distributions we'll be able to construct using Bayes' rule. Questions about how the sample mean relates to the expectation? All right. So how would you calculate the expectation of the second roll, given that on the first roll you knocked down 7 pins? Oh, okay, that was off by 2.
So you would go, we could go, if we want to just stick with the table, you would go back to the column where the first row gave 7 pins.
Right. So
then there are, wasn't it the columns where the first
right. So before we were talking about if the second roll is 4. Here we're talking about if the first roll is 7.
So you would take, I'll just ignore it too. So you would sum up all of the possible, you would sum up all the option, weighted sum of each of the options of the number you get after rolling 7 the first time. So rolling 1, 2, or 0. And then we multiply each value by probability.
Conditional probability of that.
Conditional probability. So you can take the margin 1 divided by the
joint divided by the marginal to get the conditional. So there's 4 possibilities, 0, 1, 2, 3, or 4. They each have associated conditional probability of them happening given that 7 pins were knocked down on the first roll. Those 4 conditional probabilities will sum up to 1. We take each of those 4, multiply them by their corresponding probabilities, add it all up, conditional expectation. Right? So in our code, it'd be something like that. How will we calculate the expectation of the second roll in a frame of bowling if I don't tell you what happens on the first roll? Yes.
Sum of omega times probability is equal to x2.
Right, and where do we come up with the probability of x2?
Joint probability times marginal probability. Sorry.
Where do we get the probability of knocking down x2 pins from? Where did we get it from on Thursday? Sum down the columns. This way. So we want the probability of knocking down, let's say, 2 pins on the second row. Down the columns. This margin. All right. So we take the column sums, we multiply by the corresponding values of omega, and we get that summation. So here it is in symbols. We take the joint probability, sum it up over all the things that could have happened on the first roll. And this joint probability we can expand into a product of a marginal probability and a conditional probability. Okay. So we've got these probabilities of knocking down xj pins on the second roll. Multiply it by each of the possibilities for xj in omega, of which there are 11. And that would be the expectation on the second roll. If you prefer to see this in R code, it's the column sums of our joint table to get the marginal probability on roll 2. Sum of omega element-wise by these probabilities, that's the expectation of the second roll, comes out to be 1.06 for the Fibonacci distribution of Bullen. Got it? Okay. So the expectation is a linear operator, and one way in which you can see this is if some random variable x has an expectation given mu, then what would the expectation of cx be, where c is any constant? Robert. Correct. And that can be seen from the definition. So we have cx multiplied by the probability of x. C doesn't change, so we can pull it out front of the summation. This thing to the right of the summation is just going to be the expectation of x, so it's c times the expectation of x if c is a constant rather than a random variable. Moreover, how would we come up with or what would be the process we go through to find the expectation for the sum of 2 rolls in the same frame of bowling? That's correct. And how do we know that that's a valid thing to do? Right. So you're sort of implicitly referring to a theorem that can be proven relatively easily. So in general, it's true. Expectation of ax plus by plus c is a times mu x plus b times mu y plus c, where a, b, and c are constants, x and y are random variables. We're going to prove this for the case a is 1, b is 1, and c is 0. And in order to prove it, you need to use the joint probability of the 2 things occurring. So we just amend our definition when we have an expectation of 2 random variables. In this case, the function we want is the sum, and we're weighting it by the joint probability of those 2 things occurring. Addition, we can distribute the probability here. So we have this expression, and we can break this apart into 2 summations, x times the joint probability and y times the joint probability. So we're going to do one, slightly subtle thing here. So we have a summation over x, a summation over y. The second summation only changes y, x remains the same. So we can take x and pull it out of the first summation and put it here, which is what I've done right there. And so now we have sum of x multiplied by sum of the joint probability over all the elements of y. And this is just the same as summing down the columns or whatever. We have the joint probability, we're summing over all the elements of y, that is going to give us an expression for the marginal probability of x. We do the same thing with the y term after interchanging the order of summation, and that leaves us with x times the probability of x summed over the sample space of x, which is the expectation of x, y times the probability of y summed over the sample space of y, which is the expectation of y. So we get what Robert said was true, which is the expectation of a sum is equal to the sum of the expectations. And that is not such a complicated thing to do if you go back to the definition of what an expectation is and work through it. So you need to have a conceptual understanding of the definitions of these things before you're sort of able to push forward. But once you've done that, now you can sort of take the shortcut when you need the expectation of a sum to just sum up the marginal expectations. Now, we could have the sum of two things conditional on something else, in which case we'd be using conditional probabilities here, but the application of the definition of expectation remains the same. Questions? Okay, so I just want to show this so we don't get confused by it. The outer function in R takes two vectors and the name of a function. In this case, we're using the same vector twice, omega, which is the elements of our sample space. And what the outer function does is it takes each pair of elements of these two vectors and applies the function that you give it to that pair. So here we're saying the addition function, and what comes back is a square table in this case, where the interior cell corresponds to the sum of the row header and the column header. So 2 plus 3 is 5, and 4 plus 6 is 10, etc. So the interior cells here are the sum of the number of pins knocked down in 2 rolls in a frame of bowling. Now, of course, you have 17 over here, the sum of 8 and 9, which is impossible, but that's going to get probability 0. So that's okay. But anyway, the outer function, when you do plus, basically gives you a table for all the possible combinations of number of pins you could knock down with 2 rolls, including some that are actually impossible. All right. Outer function turns out to be kind of convenient for some of the things that we're going to do, but it's not anything that deep. It's just applying a function to each pair of elements of 2 vectors. Okay. We can generalize this idea of taking an expectation beyond what we've done before by thinking of some function, any function, which I'll denote g of x, some function of the discrete random variable x, and we can define the expectation of that function with the same thing. It's just using g of x rather than x. So we take all the ways across the whole sample space that we can evaluate the function g of x, multiply them by the corresponding probability that the random variable takes that value, add it all up, and we get the expectation of the g function. Now, the expectation of the g function in general is not equal to the g function evaluated at the expectation of x. So you can't interchange the order of those things in general. That's only permissible for certain linear functions. But in general, apply the definition, you get the expectation of some function g. Now, some g functions are so fundamental that their expectations have special names. So if g is the function x minus its mu quantity squared, the expectation of g of x is known as the variance. And it has its own Greek letter, sigma squared. So it says here, how can we show that the variance is also equal to the expectation of x squared minus the square of the expectation? And it says to give as a hint, just expand out this square. So we're not going to do too much of these things over the course of the semester, but we'll do like one of them. If I can get a stupid screen. All right. We have just enough space to. All right. So if we go back to the definition and we have our function x minus mu quantity squared multiplied by the probability of x, that is equal to the summation of x squared minus 2x mu plus mu squared times the probability of x. Just expand out the square there. And so that is equal to 3 summations. We've got x squared times the probability of x plus, actually, minus 2. And mu is a constant, so we can pull that out. Okay, so now we have 3 summations. And what is x squared times the probability of x summed? Right? And what is mu squared times the sum of the probabilities of x? Right, because this is going to sum to 1. And what is x times probability of x summed? So we're going to get negative 2 mu squared. And so we have negative 2 mu squared, positive 1 mu squared. So that's negative mu squared overall. And so we're left with expectation of x squared minus the square of the expectation. Really just algebra. And it's something that follows pretty straightforwardly if you just get the definition of the expectation of a function of a discrete random variable. Let's see if we can get back. Okay, so that's the variance. Square root is defined, or the standard deviation is defined as the positive square root of the variance. So the standard deviation is not an expectation, but rather a function of an expectation. Another one, which we'll talk about more over the course of the semester, is the expectation of the g function, where g is equal to negative log probability x. And the expectation of that function is known as the entropy, which is an important concept from information theory. It was talked about on the reading a little bit for the first day. And the thing about entropy in the case of a discrete random variable is that it reaches its upper bound, like maximum possible entropy, when the distribution is uniform on a discrete space, like rolling a die. It's uniform on a 6-element space. That is going to achieve maximum entropy for a sample space that has 6 elements to it. And so we can sort of compare any other probability distribution for like weighted dies or whatever relative to the distribution with maximum entropy, which is the discrete uniform. So in this case, we could do it for bowling. We get a number 2.36. Sort of hard to interpret, like, is that big or small, until you realize that the upper bound for entropy is the log of the number of elements in the sample space, which in this case is going to be 55 or 66, can't remember which, over 2 rolls of bowling. So the logarithm of that would be sort of the maximum possible entropy for bowling. Also, when I do log, I'm always talking natural log. Never base 10, never base 2, always natural log. Anyway, so those are some of the functions that we might want to take the expectation of. Another one that we might want to take the expectation of is someone's utility function. And this is where Bayesian approach sort of ties in to what's known as decision theory. And it's often sensible to think about making the decision as doing so in a way to maximize expected utility. And that just means the following. First, you enumerate D possible decisions that you could make. You define some utility function that depends on the decision and also on some other stuff, unknown values, and maybe some additional known quantities, whatever. So you define your utility function. Then you update your conditional probability for everything that's unknown that goes into this utility function G here, conditional on everything that you do know, using Bayes' rule, of course. Then you evaluate the expectation of the G function for each of the possible decisions that you could make, and you choose the decision that has the highest expected utility in part 4. So that all seems like a totally reasonable thing to do. However, you have to know how to use Bayes' rule in order to get over step 3, to get the conditional probability for everything you don't know given what you do know, so you can stick it into your utility function that also depends on the decisions under consideration in order to evaluate this expectation. So you got to know these probabilities, or conditional probabilities would be even better, in order to evaluate the expected utility. And then, you just take the one that's the highest. So this is, sort of a challenging applied quantitative methods problem to do 3. But another challenging problem, which doesn't really have anything to do with quantitative methods per se, but is what was mentioned a little bit earlier, whoever is making the decision has to enumerate what decisions are under consideration, and whoever is making the decision has to specify what their utility function is. And this can, run into problems if someone has like agenda control. The best decision might not even get to the point where you're considering it. If you can't really say what your utility function is, you can't really do, step 3, even if you know how to use Bayes' rule to get the conditional probabilities, etc. But these are more problems in practice than they are in theory. In theory, we have a really elegant and intuitive way of making decisions when it involves things that we don't know. Like, what is the average temperature of the Earth going to be in the year 2100? There's a lot of uncertainty going into that, but we have to make decisions in light of the uncertainty about, what it is that we're going to do, today in order to, maximize utility of future society or something like that. So lots of problems with, the details of this, but the theory of it and how it ties to Bayes' rule basically just fits perfectly. We need conditional expected utility. We need conditional probabilities of everything we don't know given what we do know in order to evaluate that summation. Got it. Questions? Yeah. Right. So this is part 3 is what we're going to talk about the rest of the semester. But let's say it depends on like future interest rates or whatever. You have what you believe interest rates to be, now. You might get additional information, and that causes you to update your beliefs about the distribution as to what interest rates are going to be in the future, and you can make your decisions as to whether to borrow or lend money in the present in order to maximize the expected utility for doing something like that. So this number 3 is basically say use Bayes' rule. That's all. And we'll learn how to use Bayes' rule over and over again. Other questions? Okay. So the idea of taking an expectation of a function extends in a fairly natural way to functions of 2 discrete random variables, x and y. So if we define a g function, which is the product of the difference between x and y relative to their respective means, the expectation of that function is known as the covariance between x and y, and it can be evaluated by doing the double summation over the sample spaces of x and y, x minus its mean or its expectation multiplied by the quantity y minus its expectation multiplied by the joint probability of x and y both being true at the same time. So that is covariance. If instead we define our g function as, rather than just the product of the differences relative to the means, but also divide by the respective standard deviations of x and y. So this is sometimes known as the z transformation. Subtract the expectation, divide by the standard deviation, otherwise known as standardizing x and y. Then the expectation of that g function is known as the correlation, and it's just the double summation of that function multiplied by the joint probability summed up over the sample spaces of both x and y. Here, sigma x, sigma y, the standard deviations are constant. We can pull those out. Now we have the double summation of what we just said before was the covariance. So it is true that the correlation is defined as the covariance divided by the standard deviation of x divided by standard deviation of y. That is the definition of a correlation. And that is sufficiently important that it has its own Greek symbol. Somebody besides Christina? Rho. Symbol for correlation. And both covariance and correlation are measures of linear dependence. Consequently, if x and y are independent of each other, then they have no linear dependence or no any kind of dependence. However, it may be the case that 2 random variables have no linear dependence, and yet they have some form of nonlinear dependence, in which case they are going to be uncorrelated but dependent. So correlation is a measure of linear dependence. It has no units because the units cancel when you do the division. So it's a unit-free measure between -1 and 1, but it is only measure of linear dependence between 2 random variables. So that said, is the correlation positive, negative, or equal to 0 for 2 rolls in the same frame of bowling? Andres?
Negative.
Why?
More balls you can make, less you can make on the first triangle, less you can make.
Right. So if x the first roll exceeds its expectation, then y is going to have a tendency to come in less than its expectation on the second roll. So you're multiplying something that's positive by something that's negative, dividing by something that's positive, but anyway, the whole thing is going to be negative. Summing up a bunch of things that tend to be negative tend to get a negative number. And that is going to be the case anytime you're dealing with something that has like a fixed sum of things that are possible, like 10. So what would be the correlation between the first roll of 2 different frames of bowling?
you're saying is 0 because they're.
That is what I would be saying. Things that are independent have no correlation. So to see this in R, so here's our marginal probability for the first roll. We can get the expectation by summing omega times its respective probability. Now to get the covariance, we're going to use the outer function, omega minus its expectation on the first roll, omega minus its expectation on the second roll. So now we're doing actually two different vectors. I'm going to take each pair of elements of those, multiply them together so that it corresponds to this. So we're going to sum up of all the pairs of the products, x relative to its mean, y relative to its mean. Multiply that 11 by 11 thing by the joint probability of x and y occurring. Sum up the whole thing. That's going to be our covariance. To get the variance of x1 and the variance of x2, we just subtract the expectation, square it up, multiply by the respective marginal probability, sum over all that. That gives us variance of x1 and x2. So to get the correlation, take the covariance that we just calculated, divide by the standard deviations, which is the square roots of the variances. That gives us a correlation. In this case, it's negative 0.88. And it is ensured to be between -1 and 1. Just applying the definition of an expectation of some function of discrete random variables over and over and over again. But all you really have to know is what is the g function that you want the expectation of, and what are the appropriate probabilities to weight that by, and then you just sum it up over everything. Questions about how we calculated this correlation? Yes?
So correlation is not really the same as like x being informative.
Well,
Zero correlation.
yes. Right. So x may tell you something about y, even if they have no correlation. So the variance of y could be related to the level of x or something like that. But, you know, this summation comes out to 0 or something close to 0 when you do all this. And all these things that you know or learned before about, you know, estimating a correlation, like you type in core in R, these are really just applying these definitions with some estimate for the sample of these joint probabilities. So it's going to estimate those with like proportions or something like that, and then apply the definition, maybe a little bit of a correction for finite samples or whatever. But it's basically just taking the definition and substituting in an estimator for the unknown probabilities. Okay. Variance of a sum. So what would be the variance for the random variable that corresponds to the sum of two rolls in the same frame of bowling? So we can do an outer for the sum, multiply it by the probabilities, add it all up. We get the expectation of the sum of the first and second roll. We can get the variance of that by doing outer, same thing here, subtract the expectation of the sum, square all that, weight it by the joint probability of those things occurring, sum up over the whole joint sample space, and we get this value. Comes out to be about 0.8. And that happens to be the same as the variance of x1 plus the variance of x2, which we calculated on the previous slide here, plus twice the covariance that we also calculated on the previous slide here. And that is something that is true in general, not just for bowling. But how would we go about trying to show that, that this is something that is true in general for the sum of two discrete random variables. How would we start? Where would we start? What would we start with? Yep.
Write out the formula for the expectation.
Right. So we would write this out in symbols, and then we would do some like distributing and simplifying and other things like that that are valid for addition and squaring and stuff like that to simplify it until something like the three pieces that we had before when we were doing showing that the variance is equal to the expectation of the square minus the square of the expectation. We get three pieces like this, and we could show that they satisfy the variance of the marginal on the first roll, variance marginal second roll, plus twice the covariance between the two rolls. Right? So that's a good exercise to try. Make sure that you're facile with manipulating these definitions of expectation of a discrete random variable. All right. So last slide for today. What we've done before with bowling, it's a nice clean example. Bowling is a simple game, and we have sort of a simplified model for a simple game. And according to what we said, if there's like one pin remaining, the conditional probability of knocking it down is just going to work out to 1/2. And that might not seem particularly realistic. For a good bowler, if they only had one pin, they would probably have a more than 1/2 chance of knocking it down. But it's certainly not the most general way of thinking about that. Bowlers could vary in their ability. And so most of the distributions that we're going to work with have unknown parameters. Like, what's the probability that you knock down one pin if one pin is remaining? And how can we estimate that probability from data, again, using Bayes' rule? So the thing that we did, with Fibonacci, there was no unknowns in the probability process. You were sort of given that it's this Fibonacci ratio thing, and the only unknowns are sort of what happens on the frames of bowling. But a more typical thing to do would be to give you data on bowling and to say, how are you going to estimate the probability of a strike or whatever. And for that, we need to use distributions that have parameters in them. And so the simplest distribution with a parameter is known as the Bernoulli distribution. This pertains to a sample space that is just 0 or 1, 0 indicating failure, 1 indicating success. And the probability of success given pi is defined to be pi. So this is a very simple function. Pi being a probability, it's constrained to the 0, 1 interval. And consequently, the probability of failure is just going to be 1 minus pi. Here, we're saying this is a conditional probability distribution given pi. And later, we're going to want to try to use this to estimate pi. So we can put these two branches together by defining the probability function for a Bernoulli distribution as the probability of little x, where little x can be either 0 or 1, as pi raised to the power x multiplied by 1 minus pi raised to the power 1 minus x. And that is the definition of the probability function for a Bernoulli distribution. So what would be an expression for the expectation of a Bernoulli random variable? Robert? How do you know?
Sometimes it's going to be 0 times. Sometimes it's going to be 0, so it's going to be 1. It's going to be 1. Proportion of the answers is going to be 1 or going to be pi. So it's just
That is true, but you ought to be able to get it from the definition of an expectation, which is, right. So we have 0 times 1 minus pi. And what's 0 times 1 minus pi? And we have 1 times pi, which is, and so the sum of those two things is, right. So that is how we know the expectation of a Bernoulli random variable is pi. What would be an expression for the variance of a Bernoulli random variable? There. And how do you know that? I think it's not going to follow that directly from the definition of the variance, but it should be obtainable from the definition of the variance. How would you obtain that? So we know the variance is equal to the expectation of the square minus the square of the expectation. So what would be the expectation of a Bernoulli random variable squared? What's 0 squared? What's 1 squared? So the expectation of x squared is really the same thing as the expectation of x. What we just get through saying the expectation of x was. So we have pi minus the square of pi, which otherwise can be written as pi times the quantity 1 minus pi, which is what you said. So oftentimes it helps to use this shortcut, the theorem that we showed. All right, that's it for today. Well, we'll pick it up Thursday, learn some more distributions, and keep plugging away.
Good.